Thank you for joining us on this on-demand FEMAP webinar, where we'll look at some techniques to facilitate review of FEA results. This is one of 3 on-demand webinars that look at various aspects of the simulation process, where FEMAP plays an important role in speeding up product design and development. My name is Al Robertson, and I look after FEMAP marketing globally, and I'll be your presenter for this webinar, in which we'll look at the techniques to facilitate review of finite element analysis results. A little later on, I'll be joined by Patrick Kringziri and Ryan Catania, both of whom work in the FEMAP development group, and who will take us through demonstrations of some advanced post-processing techniques. In this presentation, we'll look at various techniques to facilitate review of FEA results. We'll start with a review of the simulation process and an introduction to FEMAP, the product that we'll use to showcase the various post-processing techniques. In particular, we'll look at how free body analysis, contour arrows, and results combinations and enveloping can help us quickly understand the results and behavior of the design, and we'll see demonstrations of these techniques. We'll also review a case study to see how a customer made use of these techniques to aid understanding of model behavior, and look at the challenges they overcame and the benefits gained. It's important that analysis keeps in step with design, where it can have the greatest effect on the design process by showing whether a given design is up to its intended job or not. So time is really of the essence as far as simulation is concerned. Typically, the simulation process starts with model geometry that has been created in a CAD system. To take advantage of this design geometry, the CAD model data has to be transferred from the CAD system to the finite element modeling environment. Once the CAD data has been transferred successfully, work can then begin to create the simulation model. When the simulation model has been completed, it is submitted for analysis by a solver like NX-Nastran, and with a successful completion, the simulation results are written back to FEMAP for review. This webinar will focus on this area and in particular on advanced results reviewing techniques. Any conclusions drawn from the results review are then referred back to the design team, who can make any necessary modifications. To maximize the effectiveness of simulation in the design process, it is essential that the whole cycle is executed as efficiently and quickly as possible. In reviewing the simulation process, you can see the pre- and post-processing components in which the simulation model is created and on which the results are displayed, and the solver components where the analysis results are actually calculated. In this presentation, we are using FEMAP as the pre- and post-processor and NX-Nastran as the solver. The solution that we'll use to demonstrate some of the workflows that can be adopted to create an efficient simulation model will be FEMAP. FEMAP is the graphics program that provides pre- and post-processing functionality to build a simulation model and prepare it for analysis by the solver, and then review results afterwards. FEMAP offers open simulation by being both CAD independent, where CAD data can be accessed from just about any source, and solver neutral, in that FEMAP can create simulation models for all the major commercial solvers, with a high degree of integration with the Nastran solvers. The modeling and visualization capabilities are all accessible within an easy-to-use and intuitive user interface, which brings many benefits, including increased productivity, a reduced learning curve, and training overhead. There is also a powerful customization tool in the form of the application programming interface that can be used to customize workflows, or as a complete integration platform. FEMAP offers a lot of in-depth FE modeling capabilities and is designed by engineers to solve complex engineering problems for engineers. FEMAP is part of SimCenter, which offers an unparalleled portfolio of solutions covering multidisciplinary and multi-physics solutions, market-leading solvers, industry-specific applications, and analytics capabilities. We can think of the portfolio as consisting of solutions that fit into 3 broad categories: 1D or system simulation solutions, 3D solutions that include both existing and new products, as well as CFD capabilities from CD Adapco, test solutions, and engineering services. For the system simulation, test, and engineering capabilities, we refer to existing offerings within the STS business segment, including market-leading products such as LMS Imagine Lab, LMS Test Lab, and LMS Engineering Services. In the 3D simulation area, we have several products, including SimCenter 3D, as well as solutions in NX Nastran, FEMAP, LMS Virtual Lab, and LMS Samtech. We will also position CD Adapco solutions in this space. In a recent survey of over 160 manufacturers, independent analyst TechClarity investigated the challenges that companies experience with simulation and documented the findings in a white paper entitled Addressing the Bottlenecks of FEA Simulation. A link to the TechClarity white paper can be found on the FEMAP website, femap.com. All of the post-processing challenges identified by TechClarity are related to the overwhelming amount of data involved and the time required to view them. Companies need better ways to work results to more efficiently interpret them. Adding to the time required, the results are not likely to be in a format that is meaningful to management. And so more time must be invested to arrange results in a way that is more easily understood. TechClarity goes on to observe that top performers take advantage of tools to help them quickly sort and review the results, in particular, to visually filter results, use interactive tools to help sort the results, and export results to other programs such as Excel so that they can be used in additional calculations. As models continue to get bigger, the amount of results data produced by the solver also increases. When you also consider performing a more advanced type of analysis, such as a dynamic response or nonlinear analysis, then the data created increases even more, as these types of analysis produce incremental output data in steps of time, frequency, or loading. With a large results database to deal with, the time to access the data increases, and the database files themselves become unwieldy and difficult to manage. This gives rise to various challenges such as long import times to read in the results data, increased memory usage in processing the results data, and managing the consequentially large database files. FEMAP offers a lot of flexibility in accessing results data post-analysis. It is possible to load all the results into the FEMAP model database, which maintains a single file containing both modeling and results data. When you import results created by the solver into the FEMAP model database, the database itself obviously increases in size and ends up consisting of the original model data, the solver created results data, and some further address data to aid results data access. Import times can be significant for large results files, and the data can only be accessed through the single database. However, data management with this option is simpler. Another method of accessing results by attaching results databases is also available. This allows the database files, model and results to remain intact, as the data is not required to be imported, though the address data for the results is still added to the model database. Data access through attached databases is much faster, and greater flexibility is possible by attaching multiple results files simultaneously. In a case where you can attach to a large number of results files, it's clear how this can help the demands on storing the FEMAP model to a minimum, speeding up file open commands and keeping FEMAP's memory footprint lower when running. Another issue is the ability to visualize the results effectively. As we've seen, the amount of results data created by the solver can be potentially huge, which makes the task of going through and reviewing the data much more onerous. For the sake of speed, this requires a set of tools that will allow you to review the critical results data efficiently. These tools should also help you comprehend the behavior of the design and allow you to communicate the findings effectively. FEMAP helps by offering a wealth of capabilities to help you view the results and get the crucial information about the behavior of the design quickly and efficiently. The arrow plots capability in FEMAP allows you to display the results you want to see in a clear and well-defined way. You can also transform output vectors into other coordinate systems very easily using FEMAP's post-processing toolbox. Vector selection is made easier. You specify a single contour vector and FEMAP will automatically select the appropriate output vectors to display, as well as the correct orientation for relevant elements, creating an arrow plot that greatly facilitates results data display. Furthermore, individual components can be selectively turned on or off. Display styling is set automatically based on the selected output vector or overridden as desired, and axial and shear components can be displayed or the resultants. Also, output can be listed to the data table, where the data can be evaluated further. As previously mentioned, the data table is a powerful method of manipulating output data in FEMAP. You can unlock the data table and send either modeling or results data to it. The data table allows you to sort, filter, and evaluate data that it contains. You can use it to rank results or compare data from different output sets or models. You can also copy the data to the clipboard and transfer it to third-party programs like Microsoft Word and Excel for further processing, then copy the data back into FEMAP again. Let's hand over to Ryan now and see a demonstration of some of FEMAP's post-processing tools. In particular, we'll see how easy it is to create and manipulate contour arrow plots with on-the-fly vector transformations, and how to use the data table to transfer data to and from third-party products.
Transforming output vectors in FEMAP is very easy when you use the post-processing toolbox. Here I have a model that has beam and plate elements, but what I want to do is I want to play with some transformations. So right now I'm using the plate X membrane, plate Y, and plate XY in a 2D tensor plot, or a crow's foot plot. So what if I want to quickly transform this into the global coordinate system? Right now I have no transformation happening, but if I quickly drop down, you can see FEMAP updates live and allows you to quickly go through multiple transformation options on the fly. Any number of rectangular coordinate systems or even spherical coordinate systems can be transformed from this drop-down box. Bring this back to your material direction. You can do it along a vector. If I look at a different kind of output, let's take a look at something like principal stress. I'm going to limit my output to just plate vectors for now. My major principal stress shows me the principal stress angles based on these vectors, and it picks up both the major and the minor. You can contour the principal stress angle if you want. It's also showing you that direction. If we also look at the beam elements, we can do some interesting things with them as well. So here I have my beam elements. We see the coordinate systems I have defined there at the bottom. Let's change my post-processing output to something like beam axial force. So here's the beam axial force, and based on my contour settings, my arrows have shown me the axial force as well as the plane 1 and plane 2 shear force. What's really useful here is my arrow display mode lets me quickly switch between something like automatic and something useful like shear YZ over axial X. Now, in addition to the axial force, I can display the combined shear force. Let's take this a step farther and let's go out of beams and let's instead look at the constraint force. T1 constraint force, let's bring my plates back into it. So now T1 constraint shows me that I've picked up on those constraint vectors, both for my beams and my elements. You can see that the coordinate systems I had defined show me all of my constraint forces along those coordinate systems. I can very easily bring these back to a transformation into the global rectangular. I can take my transformation out completely. I can bring it into spherical and many of the other options that we talked about before. With these settings, if I want to save these or do some further processing in an application such as Excel, I can open up my data table and I can do a list output contoured results to data table. Now I've got my T1, T2, and T3 constraint forces easily summarized based on what I have contoured. I can copy this, I can bring it to a different Excel, I can save it to a CSV, I can add more vectors. I can continue on post-processing to my next output vectors.
Output sets can be organized into analysis studies to help order the output data into more understandable groups. These studies can be created automatically when importing or attaching results data, or manually from existing data. Organizing the output data in this way makes it easier to find, delete, or operate on a collection of output sets from analysis runs. For example, you can group output sets from statics, modes, and time steps from a transient analysis into separate analysis studies and operate on them individually. Animate Study allows you to create a multi-set animation using all the output sets in a study very quickly. Envelope creates a complete output set envelope using the selected type, max, min, or max absolute, for all the output sets in the study. The result set processing data surface is also available. Like the load case combination data surface, different factors can be applied to each output set using a spreadsheet-like form. For the result set processing data surface, there are two ways of creating the data for this data surface. Create all immediately, which creates all of the data needed for the combination envelope sets immediately and stores them in the database. This will require a longer initial creation time, but subsequent access to the data and results display is faster. Second is as needed or temporary, which creates the data on the fly. This data is not stored in the database and is only kept temporarily. The initial creation time for this method is faster, but subsequent access to the data and results display may potentially take longer. Once you have selected all of the data sets to be taken into consideration, a spreadsheet-like form appears in the Data Surface Editor dialog. Here you can determine the type of combination in the drop-down menus of the Operation column. The types of combination include linear combination, max-min, max-absolute envelope, and the set ID of the same. The Create command on the context-sensitive menu is used to create the processed result sets. These new result sets then appear in the model info tree. The icons indicate the chosen creation or storage method, either as needed temporary, open envelope, or create all immediately, closed envelope that we described earlier. Let's hand over to Ryan now and see a demonstration of using results combinations and enveloping, and see how these tools can really help to manage the results data and provide an insight into model behavior.
I have some data I'm going to copy out of Excel. These are my load combinations that I want to create, and using the new function table editor, I can do this really quickly. Let's open this up. So dropping this down, I can hit the load set combination table, give this a descriptive title. For all the load sets that I want to choose, I have this entry table format. Quickly pasting from Excel lets me create these almost immediately. I can do the same for results. Make a table. Results. Now if I come back to Excel, I have these set up for the combinations that I want to create. Copy again. All I have to do is drop down what kind of combinations I wanted to make. We'll use linear combination for these. And boom, I have results. Let's pin this for now. I can post-process from the model info tree. We can also use the function table editor and make envelopes really quickly. Let's turn on some max envelopes. Let's make one min envelope. You can see my create this. It's going to ask me to delete the existing. I don't want to delete them. And now I immediately have envelopes to look at. Now this is an envelope of the linear combination. And so it will be different than choosing simply envelope max. We could do a quick combination. Let's look at some of those results in the data table. Fly this out. List, output, results of data table. Let's do those first two. The envelope we just created and the envelope we used from the info tree. Von Mises. We can see our summary at the bottom here. And that max value of what we created in the model info tree lastly shows our max of the two that we selected. And the max envelope we created from the function table editor is the max that's already got a linear combination built into it.
Another issue is the ability to clearly evaluate running loads through the structure. Model and results comprehension can be very time-consuming. To help to do this, FEMAP includes the free body capability, which accesses and visualizes the grid point force balance output data. You can generate free body diagrams, interface loads between components in the model, and calculate and view section cuts. Grid point force data recovery that is calculated by the solver provides some very useful output that helps to determine load paths through the structure. FEMAP provides some extremely powerful capabilities that work with this data to provide free body diagrams for parts and components, balancing loads at section cuts in the model, and can show interface loads between components in the model. Let's hand over to Patrick now and see a demonstration of some of FEMAP's free body post-processing tools. We'll see how you can easily visualize the grid point force output to efficiently determine load paths through the structure and set up free body diagrams, section cuts, and interface loads, and see how these tools can give you a clearer picture of internal forces.
Free bodies in FEMAP provide an easy way of visualizing and performing calculations on grid point force balance output that's returned by the solver. Now, in order to use the FEMAP free body tools to their fullest potential, we want to make sure that the force balance output has been turned on. In this particular case, we're looking at the Nastran output request, but this is going to be available for other solvers as well. FEMAP can work with a reduced set of data using only the applied load and constraint forces. However, when doing that, it's only going to be useful for looking at a balanced set of forces and moments that's applied to the entire model, rather than being able to gain any insight into what's happening internal to the model at a nodal level. So let's start off by taking a look at the post-processing toolbox, and within that, the free body toolbox. Just like the deformed and contour toolboxes that are found within the post-processing toolbox, the free body toolbox provides a centralized location to easily create and modify any free body within FEMAP. It's all located in one place. One important thing to bring up here is that FEMAP can create and display any number of free bodies simultaneously. Unlike other packages, you're not limited to just a single free body display at one time. In addition to that, what's probably even more important is that the free bodies that you create within FEMAP are stored with the database. This is important if anybody wants to take a look at a model at a later date that has a free body created. They can just pull up the model and the free body is already there. There's no time spent trying to figure out specifically what nodes and elements may have been used to create that particular free body display. I'm going to create a new free body by going into the free body manager and then clicking new free body. Here we see the new free body dialog, and then we also see the three basic types of free bodies in FEMAP. The first being just a basic free body, the second being an interface load, and the final being a section cut. One thing I'll point out is that within this dialog, any of the options you set here, be it the display mode, the vector display, or the free body contributions themselves, these aren't set in stone. You can change these later on at any time within the toolbox itself. And this is just a starting point for creating a new free body. So let's take a look at just the basic free body only mode. With the standard free body display, the user needs to select just the elements that relate to the portion of the model that they're interested in. So here I'm going to select the center portion of the wing, not including the two ribs on either side. And what FEMAP does is it will go through and find all the nodes on the boundary of the selected elements, and the resulting plot is showing the forces that are acting on these selected elements. And that has to do with the default contributions that were selected back when the free body was created. Again, we can change them here, and we can see that by default peripheral elements is selected, which means that what's being shown is the elements that surround the ones that we selected. Those are imparting a load onto this structure. If we were to reverse this and show free body elements, meaning the ones that we've selected, rather than the peripheral elements, we'd be looking at what the selected elements are imparting onto the surrounding structure. Now, let's take a look at the second type of free body display, and that's going to be section cut. Before we do that, I'm going to turn off the visibility for the free body that we just created, just to make things a little more easy to see. So let's go back into the free body manager again, create another new free body, but this time let's do an interface load rather than the standard free body display. Now, the main difference between interface load and free body is that the interface load is designed to have an imbalance based on the selected nodes and elements, and therefore a total summation vector is going to be drawn. With the standard free body mode, because FEMAP will auto-select all the nodes along the boundary of the selected elements, when you do a summation of the total vector summation at each one of those nodes, everything ends up being equilibrium, so there's no need to draw a total summation vector. Whereas with the interface load, we're only going to be selecting the nodes across the boundary of interest, so there is going to be an imbalance when you do the nodal summations at each individual node. Now, in this case, let's say we're concerned with the load transfer between the skin to this spar here. So what I'm going to do is select these elements along the upper skin as it goes to the aspar, but I'm also going to select the three beam elements represent the flange from the skin to the spar. Now, nothing's been drawn yet because we need to also select the nodes, and then I'm going to select the 4 nodes along the boundary of the skin to the spar. Now, because this isn't free body mode, we're not going to be we're not automatically selecting these 4 nodes. And then there is going to be an imbalance there. So FEMAP asked me, do I want to place the total summation vector at the center of those nodes? I'm going to select yes. Now we see that there's the nodal summations that we saw previously that are going to be used in the calculation of this total summation vector. Let's turn off the nodal vectors just to make things a little easier to see. And then we see here that we have this total summation that is 1205 roughly down the length of that spar, 40 in plane with the web, and 25 as a pull-off load. Now that's okay, but what I want to do here is actually get things a little more in line with the spar. So I'm going to create a new coordinate system, locate it using the XY locate method. The origin is going to be at that node there. Point on the x-axis is just going to be down the length of the spar. And then for my point on the XY plane, I'm going to pick something that's just roughly in plane with the skin. Now we can see here that as a result of that, the shear load is now a lot more in line with that spar, and then it's now 1186 in line here, and then a 215 in plane with the skin, and then a much less significant pull-off load, and which kind of makes sense because in this particular model there was no pressure load applied to the skin. The final type of free body mode is the section cut. So let's create another new free body, this time creating a section cut. With a section cut, the user will define a cutting plane, and FEMAP will automatically determine the nodes and elements that lie along that cutting plane. So in this case, let's select a cutting plane that's in the XY plane, and then the normal is along the Z-axis. And rather than looking at forces, let's look at the moments for the total summation vector, and let's turn off the nodal vectors. We can use the location slider tool to move the location of the cutting plane along the path. Now, as the cutting plane is moved, FEMAP will automatically select the elements that are cut by that cutting plane. However, unlike with free body mode, the nodes that are selected for that are only the ones that roughly lie on that cutting plane. So like an interface load, you're going to get an imbalance across there. And as we look, we orient this like so, and then if we take a look at the X bending moment from the root, as we go out to the tip, the numbers gradually decrease as we go down to 0. So you can see that the section cut mode is good for making a quick estimate of things like shear or bending moment along the length of a structure. Equally as important as all the different free body displays that are available is the ability to take the data that's used to create the free body display and export it to a different another destination for further analysis. So let's take a look at the interface load free body that we created earlier, and then I'm going to list the free body data, the nodal summations, to the data table, if we select them all, copy it, this data can easily be copied over to Excel for further analysis.
Let's look at how Lockheed Martin Space Systems used FEMAP with NX Nastran for the design of NASA's multi-purpose crew vehicle, Orion, and how they overcame some challenges with the analysis of large models. In particular, analyses that required over 900 load cases on large models of up to 1 million elements, giving a high volume of results data to sort through. Keys to success included more efficient workflows due to the tight integration between the solver and the pre- and post-processor, ease of use of the pre- and post-processor with its powerful visualization capabilities, ability to import Pro-E CAD data, and FEMAP's API, which allowed the creation of customized functions. As a result, the company successfully completed complicated case studies in a short period of time, saw improved efficiency due to FEMAP's geometry manipulation and visualization tools. Also important was the ability to sort through the many load cases using the data ranking and free body functions, and FEMAP's API, which allowed automation of routine tasks, saving time and increasing accuracy. In this webinar, we've been focusing on techniques to facilitate review of FEA results using FEMAP. Besides post-processing capabilities, FEMAP also offers comprehensive pre-processing functionality to aid FE model creation, analysis setup, and solver interaction. FEMAP, being Windows-based, is an intuitive and easy-to-use application. As we've seen, it provides comprehensive pre- and post-processing functionality and, as a standalone application, can link to just about any CAD source and interact with all the major commercial solvers. One other point to mention is that FEMAP has a very powerful application programming interface that can be used to automate simulation processes and integrate third-party solutions. This webinar is the third in a set of 3. The other 2 webinars are still available, and you can catch up with them and view them if you missed them earlier. They are how to create an efficient simulation model and when to use nonlinear analysis for buckling. Now we're in the closing minutes of this webinar. If you have any questions, you can pose them on the FEMAP community site. To get there, first go to the FEMAP website at siemens.com/plm/FEMAP. In the lower right-hand part of the page, you'll see the Quick Links tab, and the top quick link is for the SimCenter FEMAP community site. Then create a post for your question, and please reference this webinar. The FEMAP community site is constantly reviewed by Siemens FEMAP technical and development staff, as well as numerous FEMAP super users around the globe, who are always willing to jump in and help. If you'd like to find out more about FEMAP, you can call this number to speak to us directly. You can also find out more about FEMAP by visiting the website at siemens.com/plm/FEMAP. There is also a free 45-day trial available that will allow you to access the full FEMAP with NX Nastran software programs and try out the simulation capabilities on your own models and datasets. Thank you for your attention during this webinar, and I hope it was informative.